problem, I'll be discussing it fast. So we're given here a pump and we have an impeller. Now this is opposite to a turbine, but I will discuss as we go. So we have 13 centimeters of our inner diameter, 30 for our outer diameter. That is practically here as our inner diameter and here as our outer diameter. Something to note is when our air goes inside, or our liquid goes inside, or fluid in this case, it will be spun around here and it will exit through this channel here. So the control volume that we will use is practically something like this. This gray shaded area here is our control volume, and as fluid goes inside here, we have a width of the impeller and as well as the circumference of this area here. And then when we have our outlet, it's the same idea. Looking at it at 3D, it's much more easier to idealize. So here I have the circumference, then here I have the width. Now if you take the surface area of this thing, or we just do 2 pi r, which is our surface area, then we multiply this by the width of the starting part right over here, we can get the area at the beginning. Then we can do the same thing for the area at the out. So we are able to find our area at here and our area at here. Now going to our formula, power is equals to torque times our angular velocity. We know that torque is equals to the moment, and then our angular velocity can be found out since we are given the revolutions per minute. Now using Euler's formula, which is right over here, we have the torque, which is equals to the mass flow rate times the out minus in our momentum, angular momentum. We have our mass flow rate, we have our R2, we have our R1, we don't know these values. Actually, we are given volumetric flow rate, but we have water as our liquid, so we can practically take the mass flow rate is equals to the volumetric flow rate times the density. So we have mass flow rate. Now remember the idea of the surface area of the cylinder. Now we have our volumetric flow rate given here, we have our velocity that we are trying to find, and we can find the area by taking again the circumference of this, then the width, getting the surface area of the cylinder right over here. Transposing everything and solving all of our values right over here, we can get these two values for V1 and V2. Now we have a velocity which is going this way, then it leaves this way as stated in the problem. Now I want you to imagine when our fluid goes inside, it goes this direction first, but then as it exits right over here, more air particles around here are also pushing it this way. Therefore, our resulting velocity should be slanted going this way. Luckily for us, we are given the angle. Now, if you can notice, we have here as our point, V1 is practically 0 if we have a moment for this, because it's not perpendicular. But for this, we can take the tangential and we have a moment for this velocity. So simplifying this and this even more, V1 tan theta is 0 because there is no, it's not perpendicular. Then also this, it's going to be simplified to this. We practically got our angular velocity, then our mass flow rate. Now plugging all the values, we have our mass flow rate, we have the radius 2 and radius 1, which is just our outer diameter and inner diameter, both of them divided by 2. Then our velocities, which we have found to be 7.87613, leaving, this is the out, and this is our in. So we can have that as 0 right over here. That gives us a torque of this amount. Now placing that to our power or our shaft work, it's going to be this times our angular velocity, which we have solved as rad per second, and simplifying it, we have this.